let's do let's start working with another M file. Remember, guys, that the MATLAB programs, okay? So MATLAB programs, the extension of math programs are .m. Okay, so that's why the people call them M files. Do you remember, guys? Imagine that I have a variable, a matrix A that is going to be one, let's say 1, 2, 3, 4. Okay, do you remember I tell you guys, can you please create 2, 4, 1, 3? So basically what I'm doing is I'm flipping the columns, or we can create another matrix that is starting with X again. It's going to flip the rows. Okay, let's do this in MATLAB, and then let's create let's create a MATLAB program. Create something that we can call, let's say, example flip. Then what I want is that you enter a matrix. So your program should be able to accept a matrix as data. And your program should return, let's say, uh, let's call A up and down, A left to right. So these are the two matrices that your program is going to create. Okay, let's say 3 minutes to do this stuff. Two more minutes and then we solve it. Just create an M file, guys, that allows you to flip a matrix up and down and left to right. Okay. Okay, you are done, guys? Let me share. We can create a function, guys. Let me create a new one. Okay. So remember, we can create a function. How do we create a function in MATLAB? We simply start writing function. Then we write the name. Let's call it x. Let's call it flip. I will call it 25. Okay. And then you start writing your code. Correct. Remember, at the beginning, you can write some commentaries or some things that you want the people know about your program. This program. So this part here is what the people, when they do a help, this is what help shows. Okay, the first part, the first commentaries of your program is going to be shown by when someone types help. Okay, so we want this matrix, this program to accept to require a code, a matrix, right? So A is a matrix. Okay, and we want the program to return a couple of things. Remember, when we want to return, we need to do bracket, bracket, and we can call it A up and down, A left to right. So these are names. Now, how do we create A up and down? So let's create A here equals 1, 2, 3, 4. So this is my A. How do I create the transpose of this one here? So let's do this here first. Let's create A1. How do I move the second column to the first position? Someone.
Sorry, to move what?
I want to move the second column to be the first column. We have done this before. How do we do that?
It's A, open
Yep.
the um
Should
all
be,
rows
yeah, all rows.
from and until 1.
And so I need to decrease by 1 and stop at 1, something like that.
Yeah.
Do you agree, guys? Okay, so this is the first part of your code. So this should be equals this one here. And A left to right should be equal to what then? I will write this directly here. So what I need to change, guys? So now what I will do is I will be changing the rows, correct? So what I can say is, okay, from the last row to -1 up to 1 and give me all the columns. Agree with me or not, guys?
Yes.
And that's it. That's all your program. It's very, very straightforward program. So remember, we're going to complicate our lives a little more later. This is the name of my program. This is the input, and these are the outputs. Okay. So the names here, guys, what I'm doing, the names here need to coincide with the variables that you are creating here. Now, how do we run this program? So let's save this program first. How do we run this program? Remember, guys, that the programs that have inputs and outputs need to be run from outside the program, let's say in the command window, or this can be called by another programs. That's what we're going to be doing in 1 minute. Okay, let's run first that domain an easy program. Okay, I have created my matrix A. A is this one here. So I can simply call my program and run it. What happens here? That's it, nothing, it was nothing. Okay, can you be sure that this works, guys? We're gonna do something more with this matrix, with this program, simple program.
I just have a question.
Mhm.
Is it okay if we just do like flip up down A and flip left
Yes,
right
of course.
A? Okay.
Yes.
Is
Just
there a benefit of doing one
no, no,
versus the
no.
other?
No, nothing, nothing. I just wanted to create this program, and we're gonna link this program to another program in 1 minute. No, that's perfect. And they should be, they must be exactly the same, correct?
Yeah, they are. I have mine as flip up down and flip left right. So I
Yep,
mean,
that's
I guess
good.
I'm just wondering for the rest of the class, should I just use what you're
No,
using or
no, no, no,
keep
no, no.
what I have?
You can use whatever you want.
Okay,
The easy
great.
for you, sometimes the people don't remember the flip up and down or flip L and R, so better to create their own programs. Do you agree? But if you remember, that's perfect.
Gotcha. Okay, thanks.
Okay. Okay, guys. So now let's go back to my paint and let's create another M file. So what we're going to be doing now, guys, is we can have an M file. Okay, let's call program one. And this program one can do a lot of repetitive actions. Okay, so you don't want to be writing repetitive actions all the time in your code. Your code is going to be too heavy. So instead of doing repetitive actions, what you can create is you create another program. So you create program one or program two, let's say. That is going to be called by P1. Once it's called by P1, it's going to return something. Do you agree? Or P2 also can call another program that is called P3, and P3 does something, returns this to P2, or returns this to P1. So we're going to create this nested programming, okay? Nested programs. So let's create something very simple. Let's create a program, okay? Okay. Create a program, an M file, that accepts, let's say, two matrices. Let's call them matrix A and matrix B, okay? And what I want is simply do the following, okay? Okay, A and B, same dimensions. For now, let's assume A and B have the same dimensions. What I want from you guys is to do A plus, so let's call this C. I want C simply to be A plus B. And I want D to be this one. Okay, so let's create a couple of matrices. 1, 2, 3, 4. B is going to be equal to 5, 6, 7, 8. Okay, so what I want, D is going to be basically 2, 4, 1, 3 plus 7, 8, 7, 8, 5, 6. Okay, using your example flip, well, in my case, this one here. okay? And return C and D. So now what we'll be, call this program, guys, for example, example call prog. Yeah, call one. Yeah, this is going to be my name. Oh, okay, guys, so what we are doing, I need to repeat this because I was not recording. So what we are going to be doing now is we are going to be nesting programs. So one program, P1, can have several routines that are repetitive. So instead of repeating every single routine in the same program, this is going to be make my program very heavy. What we can do is we can create different programs. For example, program 2 can be called by program 1 and return some outputs. Program 2 also can call P3, and also P1 indeed can call P3. So these programs are a kind of independent programs, okay? And this is the way we're going to be working. So for this, we're going to be creating an M program that is called an M MATLAB file example call1.m. What it does is accept two matrices. For now, let's assume that they are same dimensions, and the examples are here, A and B. And what I want from you simply is compute in your program C equals A plus B, D equals, take a look using A. So what I've done here is I have shifted the columns, and for this one, I have shifted the rows, and simply at the end of the program return C and D. Okay, so let's do this in, let's say, 3 minutes. But call this one here. So you need to call this program here. Okay, when I say call, what I'm saying, guys, is basically you need to do this in your program. Okay, this is calling. So I'm calling this program here. The only difference between calling from my command window is that now I will call the program from my new file, from my new program. Okay, let's say 3 minutes, guys. One more minute, guys. Okay, so let's try to do this. Okay, let me continue recording. So let's create a new file, a new function. So we're gonna call this what was the name of this one? It was going to be called example call one. Okay. So my function is going to be example call one, and I need to accept two matrices, A and B. Then what I need to do? Well, I need to compute, estimate A plus B. That's easy, correct? So and we're going to call this C. C equals A plus, oh, plus B. It's not B like that, it's caps B. And then I need to first compute up and down of this one here. I think it's up and down.
Professor, should we see Paint or MATLAB?
Oh, MATLAB. You're not seeing
Okay.
that?
No, we
Okay.
see Paint.
Yeah, no. It's good to let me know because I don't know what's going on with my computer now. Now, do you see this? MATLAB? Guys, MATLAB? You're seeing MATLAB?
Yeah.
Okay, perfect. So what I have done is I have created a function. This function is going to accept two matrices A and B. For now, we are saying that these two are going to be the same dimensions. Okay. Then I am simply going to estimate A plus B. I simply sum A plus B. And I will create a matrix D. But before that, what I need to do is, so I need to do, this is what? We're flipping columns for this one here and flipping rows for this one here. Okay, so what I will do is the following, guys. I know I have created this program, right? And this program creates immediately creates the up and down and creates the left and right. So how do I call this one here? Well, calling the program means doing this stuff. So we'll call this one here, and I will put this one here, in here. So yes, I can call it. I will call this A up and down, A left and right. And I will call again the same program. But now, what I will import is B, and I will change the names here. This is going to be B and B. So basically what I'm creating here, guys, is up and down, left and right of A, up and down and left and right of B. And once I have this one here, I can simply compute D that was equal to, I think it's AUP plus B LR. Do you agree, guys? It's doing problems this one here. Oh my. I don't know what's going on with my MATLAB now. 1 second, please. If you can be doing your own programs, please, guys, so we can move forward. No, I don't tell me. Oh, here we go. Let me save this one here. And then I need to return C and D. So this is the way, guys, in which we call from one program, we are calling another program. This program does something repetitive and then simply returns the results here. And then I simply use the variables that I want, variables that I need, and then I simply create whatever I want. Make sense? So I think I have created matrix A already. And matrix B is going to be equal to 5, 6, I think 7, 8. Now, how do I run this program once more? Once more, if I want to run this program from my command window, I simply copy this one here. Just paste it there. Now, guys, if you want to check if if the program is going correctly, how can you stop the program at a given point in your code? Do you remember that? Well, you use a bullet point. Okay. Simply click on the numbers here, appears red, and then we should be okay. So let's run this program from here. And the program does, you see that this is correct, calculates your your AUP and your ALR, and then that's it. So you can run this one here, you continue, and then you obtain your C and your D. Questions? No questions? It's clear?
Yes.
Okay. So what I will do now, guys, is I will send you a couple of files via email, and then we're going to analyze them. Okay. So give me 1 second. Guys, I have sent to you a couple of files. Let me close this one here, and I can close this one here. So 3 or 4 files I sent you via email. Can you check that, please? And can you download them into your class materials? 2 minutes to do that. Okay, do you have it? Do you have them?
Yeah.
Okay, perfect. So before going to the programs, guys, there is something more that we need to learn. Is what is called the if else conditions. And we're gonna start using them in a minute. So guys, the if conditions work in the following way. If, so you want to write something here, something happens. Else, something happens. And end.
Professor, I'm seeing MATLAB.
Oh, give me 1 second. Let me share. I'm sharing a complete screen, so why is not accepting stuff? Yes. Okay, so what I was telling to you guys is we need to understand, first of all, what is the is-else condition. It works in the following way. You put a condition. If you write a condition here, then what happens if this condition is satisfied? If the condition is not satisfied, happens something else, and end. This is a typical if-else condition. Now, you can have a much simpler version. If something, and there is no other condition. There is only one condition. Or you can have more complex conditions. You can have if, else if. So you write a condition here. You write another condition here. Let's say condition 2. And you can have as many else if as you want. But the last one should be a simple else. And then you close the loop with an end. We're going to work with this, but these are the conditions, okay? Condition K, etc. So let's do this in a program. Let me go to the MATLAB here. I think I stopped this again. So let me open this example here. Do you see my MATLAB, guys?
Yes.
Okay, so now remember that I told you A and B must be the same, must have the same dimensions. Okay, what if A and B, someone is using your program, and A and B do not have the same dimensions? This can happen, right? So what we are going to be doing, guys, is how do I test a condition? I want to test that the rows of A are equal to the rows of B and the columns of A are equal to the columns of B. Correct? That's what I want to test. What do I need to do? First, I need to have the rows and columns of A and rows and columns of B, correct? Agree with me, guys? What do I use for that? What command allows me to get the rows and columns of a matrix? Guys,
Size.
size. Okay, so what I will do is I will create a matrix of results, and I will say this is size of A. And I will create another matrix of results M1, N1, that is going to be simply equal to size of B. Basically, this is going to store the size of A, this is going to store the size of B, and then what I need to be sure is that I have my condition satisfied. So what I will do is I will ask the program if M is not equal to M1 or, where is my or? Oh, sorry, no, it's or and. Well, I can do, yeah. Where is my or here? Oh, here we go. Or N is not equal to N1, then I can set up an error. And I can write whatever I want. Oh, sorry, I need to do, or is in this case is double. Do you agree, guys? This implies that if number of rows of the first matrix is not equal to the numbers of rows of the second one, or the number of number of columns of the first one is not equal to the number of rows of the first one, I need to send an error. And the error is simply you write it like this: matrices do not have the same dimension, semicolon, and that's it. Okay, this is one use of if conditions. So let's create here, what was my B? B. Okay, so I will create another B that is going to be equal to 1, 2, 3, 4, 5, 6. So this is B, this is A. Okay, I want to run my program, this one here, and I want to stop the program here. Okay, I will run it here. Then I have my A, I have my B. The number of rows of A are 2 by 2, and the number of columns, 2 rows, but the number of columns is going to be 3. Okay, so here we're going to ask the question: is M not equal to M1? No. But N is not equal to N1, correct? So let's put a red here, and let's run again. Let's continue running. You see? You see what happens, guys? MATLAB is going to tell you, error, your function matrices do not have the same dimension. So this is what is going to be announced. Make sense to everyone? This is one use of if command, and this is the way you can communicate that someone has made an error when using your program. Okay? Questions? No questions? Okay, guys, so we'll close this matrix. Can you open the files that I sent you? Let's open only one, Census Data Analysis 23, and let's open the other one. Let me check which one I will open. Gender selector. Just give me 1 second, guys, please. Okay, guys, let's continue. So let's take a look to what happens with this program. Okay, this program here uses this data. So if you want to see the data, let's plot the data in the command window. This is data. I think it is the ID of the people. This responds to the age of each individual, and 0 is male and 1 is female, let's say. So you have ID, age, and gender, right? So this is the matrix that we have. Sorry, age, yes. Okay, so this is the data that we have, and we are going to create this program. Oh yeah, here we have it. We have age, gender, 0 if male, 1 if female, 3 years of education. Sorry, yes, it's years of education. It's not. So wait a second. So 1 is age. Doesn't make sense. The gender and years of education. I don't know what is years of education. Perhaps years of education is going to be here. Oh, no, no. Years of education are going to come later. Okay, so what we have here is ID, age, and gender. Okay, what we're going to be doing, guys, is simply doing what we did last class, one by one. So now what I want, for example, from this one here, I tell you, hey, guys, give me the number, give me all the males in this selection here. Okay, can you do that very quickly, just to practice? Give me the ID, the age of all the males that are in my matrix X. Yeah, let's call it M.
Sorry, so you want us to find the ID
Males,
age
yeah.
for males?
Yes, I want ID, age, and so I want the three rows basically of all the males.
Okay, gotcha.
Okay. Okay, 1 minute, guys. Okay, if we want to do this manually, guys, what do we do? My matrix is called X, right? From X, I need to select all the rows. Then what columns do I select? They need to satisfy a condition, right? So what is a condition? We can say X, sorry, what do we want to from X? Which row? Which row has the information about males and females?
The third one.
Third column, sorry, third row, all the columns. What I want from this condition, guys, I want this to be equal to 0, right?
I'm not seeing, Professor.
You're not seeing?
No, there's MATLAB, but it's like frozen.
Okay, so let me share this again. I don't know what's going on here. Yeah. Yeah, I was saying do you agree with this one here? I will select from X all the rows, and the columns are going to be only those that satisfy this condition. Agree with me or not?
Yep, I agree. Yeah.
Here we go. So basically, individual number 2, 3, 5, and 7 are males, and these are the ages of the males. Got it? So you need to remember this one here, guys, because we're going to start working with the data sets, and I will simply ask you to filter, modify, change, etc. So this must be very familiar to you. Okay, so I have here what I will do here in the program is I will create a program that is called gender selector 23. And what gender selector 23 is going to do is it will call this program gender selector 23, and it's going to provide X, and it's going to provide the gender, okay, that I'm interested in. So let's go to gender selector 23. So what it does is receives data, and the second argument is gender, and will return gender data. So this is an A. Okay, remember, gender, 0 is males, and 1 is females. So, and what the program does is very simple. It does gender data, what we have done. From the data that you provide here, give me all the rows and find from data position number 3. Oh yeah, I'm using find here instead of the logical operators or relational operators. Find from data equals gender and provide me the answer. Make sense to you guys? So we have done in using a NOR method. Basically, what we're using here is the find command. Okay, so I will run this one here. The same is going to be with females. The only thing that is going to be different is 1. And that's it. So let's run up to 32. Oh, there is a syntax error. Where is the syntax error? Okay. Oh, we have a... Okay, to drink. I don't know why. Okay, so let me... Oh, I think this is going to be for you. I think this is going to be... So let me right click. Let me comment this for now. Let's save this one here. Yes, and now, so let's run up to here. Do you have the program open, right? I want you to run with me, guys. Do you have it open?
Yeah.
Okay, so let's run. So do a bullet point at 32. Run. And here you have your males and your females. And you can see because the third row equals 1, 1, 1. Now, can you take a look to what is this one here? the age selector does? Can you check? So you need to open your file that is called age selector 23.
Wait, Professor, it was line 32, and what was the other stop point?
Just line 32 at this point.
Oh, just line 32. Okay,
Yeah.
thanks.
And then now go and check your age selector. So what is this doing? Okay, the question here is 0 is not okay to drink, 1 is okay to drink. Okay, so take a look to age selector, the data and the indicator. Indicator is 0, not okay to drink, 1, okay to drink. In this case, guys, what the program is going to be doing is going to use an if-else command. It's going to ask if the index, so this number here is 0, basically this implies give me, what we are asking is give me the people that is not okay to drink, correct? So we do the same, find from data number 2, younger than 21 years old. Else means that the index is 1, basically give me the ones that are okay to drink, because I know that we're looking for the people that is older than 21 years old. Make sense to you guys? Okay, now let's go to census analysis and let's stop at, this is okay, not okay to drink, so that's 0, okay to drink. Interesting. Okay, so can we run only up to here? So we have from my main matrix, I have okay to drink. I only have one male that is older than 21. And all the remaining ones in my sample are females, and here are the ages and here are the IDs. I can do the same with not okay to drink. So basically not okay to drink, instead of 1 here, what I do here is I just write 0. And the not okay to drink are these people here. 1, 2 females, and the remaining ones are males with, of course, years or age less than 21 years old. Okay, so now we can do a little more. So I want to know all the males that are okay to drink. So remember, I already have a matrix that is called males. So what I can use is exactly the same matrix, the program age selector, but now I'm just going to input the males matrix, and give me just from these guys, give me the ones that are okay to drink. So we can take a look to what happens. You see, there is only one male that is okay to drink, 3, 22, 0. In identification 3, 22 years old, male. Select all females not okay to drink. So I will use the matrix of females only, and I use 0 because 0 implies not okay to drink. So I will stop here, etc. What I'm doing here now, guys, remember, these are the females not okay to drink. And what I will do is select all females not okay to drink. Yes, okay, gender selector. Oh, gender selector is another matrix. Do you agree? Gender selector. Have we used that or not? Yes, gender selector. So what I'm doing here is females not okay to drink 2. What I'm providing them is gender selector not okay to drink. So these are the people not okay to drink. And I just select all the females. Okay, do you agree? So I'm using another program that is called gender selector. Simply provide all the data, and what this is going to be doing is selecting the females. And as soon as I'm in a not okay to drink, I know that the females selected here are also going to be females not okay to drink. So that's why I'm calling this one here females not okay to drink too. So let's move it up to here and let's take a look. You see 1 and 8 should be the same as here, 1 and 8. Okay, guys, what I'm doing here is I'm simply adding a new vector, years of education, and I'm joining years of education with a normal x. So I'm putting x is this one here. I'm adding to the bottom of this y, and then I'm asking for different things. Okay, you can explore this stuff. I will give you assignment number 3, guys. That is one assignment that asks you to modify something in this program. Okay, so assignment number 3 is going to come tonight. That is the first question is going to be to modify this program and to do some other things here. And we need to continue with more things. Questions, guys? Do you understand how to call from one program many other programs? Is that clear? Guys, is it clear that this is the way you call from one program to another program?
Yes. Yeah.
Okay, perfect. So now, guys, let's go. Now we need to go more into economics. In terms of in economics, guys, we use a lot econometrics, okay? And in econometrics, what we use a lot is a linear algebra, okay? And so let's have a very quick look on the things of linear algebra that we're going to be needing when we start working our own programs in MATLAB. Okay, so let me clean this part here. Okay, so I can continue working here. So there are some special matrices, guys. There are, for example, if you want a matrix of zeros, the MATLAB command is zeros. If you put a 3, for example, it's going to give you a matrix of just zeros, a 3 by 3. You can have a zeros, for example. I want to have a zeros, 1 row, 4 columns, for example. So this is the way, no, it's not 1.4. This is the way you do it. You have also another matrix that sometimes we use it once. The same notation. One that we use all the time is the identity matrix. The way we create identity matrix is with an I. Okay, so we know the matrix operations, we know them. So let's do this very quickly here. So we know that if we want to sum A plus B, the dimensions must be exactly the same. So if this is m times n, this must be m times n. Do you agree? The same is plus minus. Now, if I want to multiply two matrices, A times B, so if this one here is an m times n, this needs to be an n times p. And the resulting matrix, guys, is going to be what? An m times p. Do you agree, guys?
Yeah.
Of course, we have seen element by element multiplication, so we have done that already. So let's do something that is very interesting. So let's take a look to imagine we have our matrix A. Okay, I think A was equal to 1, 2, 3, 4. I don't remember, something like that. Okay, can you multiply this by my original matrix B, 5, 6, 7, 8? Can you do, let's create C is equal to A times B. This is correct, right? This M is a 2 by 2. Sorry, this A is 2 by 2. This B is 2 by 2. And I want you to compute D equals A element by element multiplication times B. I want you to test what is equal, let's see, E. So what is equal if I multiply A times I? So what happens here? So let me define U. Let me define U as 3, 2. And let me define B as 1, 4, 5. Just tell me this one here. What happens if I do U prime times B? U prime is going to be, if this one is a 2 times 1, U prime is going to be a 1 times 2. And B, no, sorry, I cannot do this here. So I can do U times B prime. Yeah. U is going to be a 2 times 1. And I will do prime here. So this is going to be a 1 times 3. So your resulting matrix, let's call it F, is going to be a 2 times 3. Now let's define another matrix. Yeah, let's say X, let's say is the same, 3, 2. And Y, let's say is 9, 7. Okay, I want you to compute G equals X prime Y. So this is going to be 1 times 2, and this is a 2 times 1. So this one here is going to be a 1 times 1. This is what is called a scalar multiplication. And let's define another one. Let's call this E equals 1, 2, 3. And let's do FGH. It's going to be simply E prime E, and 7 matrix I is going to be E, E prime. Okay, so let's say 4 minutes to do this, guys. 2 more minutes, guys. One minute. So do you see my screen, guys? My MATLAB?
Yeah.
Yes.
Okay. So A is this one here. I need to be sure that B equals 5, 5, 6, 7, 8, I think I said. Okay. So what was the first thing to do? The product, element by element product, multiplication by I. Okay. So let's call this C. C equals A times B. They can be multiplied, correct? And the dimension is going to be a 2 by 2 also. D is going to be A element by element multiplication times B. And you can see they are completely different. Remember, the element by element multiplication is this one here goes with this one here. This one here goes with this one here, etc. E is going to be what happens if I multiply one matrix times the identity matrix, I of size of A, comma 1. Do you agree with me, guys, to make it more generic? What happens when you multiply one matrix times I, the identity matrix? You obtain the exact same matrix, guys. Okay, so this is one of the properties that we have when we do linear algebra. This is exactly equal to the original matrix. Let's do 3, 2, 1, 4, 5. Okay, so I can define U equals 3, 2. I'm transposing just to make it a column. And V equals 1, 4, 5. Do you agree with me, guys? So I have my matrix U and V. They are like that. So what I will do is I will do U prime. How do I call this name? This one here is named F U B prime. F equals U times B prime. Is it possible because U is 2 times 1 and B prime is 1 times 3? So 2 times 3 is the result of this one here. And then G is the reverse. Is B. No, sorry. It's going to be U. I think you said U prime B, right? No. Oh. U prime Give me 1 second. So U prime is going to be, okay, so U prime is going to be 1 times 2. Of course, I cannot multiply. I have another vectors, I think. I gave you another vectors. Yeah, this one here, x 32, y 97. So let me write x equals 32. And y equals 97. Okay, let me print x and y. And then what I can do, fg, I think is going to be x prime times y. You see? This is one x prime. This is going to be 1 times 2. The other one is 2 times 1. So the resulting matrix is 1 by 1. This is what is called the scalar multiplication. And then I have E, and this is a very important example. E equals 1, 2, 3. I say that. Yeah, X. So matrix E equals 1, 2, 3. I want this transposed. Now, what happens if I do E primes E? I obtain 14. Do you recognize this formula, guys? How many of you are doing economics here? Guys, how many of you are doing economics?
Me. I am.
Oh, Simone, Julia, and Anna, all of you are doing economics? Are studying economics? Yes, all of you?
Yeah.
Okay, great. So do you recognize this formula here, this form here? In econometrics, guys, a simple model of econometrics, what we try to do is we try to minimize the sum of a square of the errors. Do you agree? That's what we try to do. And this is the way a column vector is presenting the sum of square of the errors. So take a look to E prime times E. So let's take a look here, okay? Look, E prime E. So what we are doing is 1, 2, 3, and E prime times E, 1, 2, 3. What do we get? Multiply 1 times 1, 1 square, plus 2 times 2, 2 square, plus 3 times 3, plus 3 square. Do you see? So this notation here, when you have a vector, E prime E is simply the sum. This is what we also call the sum of squares of the errors. Now, what happens when we have E times E prime? So now I have E, 1, 2, 3, times E prime, 1, 2, 3. So the resulting matrix is going to be what? What, guys? The resulting matrix is going to be what? If this is a 3 times 1, this is a 1 times 3, this is going to be a 3 times 3. Agree with me or not, guys?
Yeah, I agree.
Okay, so the first one here, take a look to why this matrix is so important for econometrics. This is 1 times 1, 1 times 2, 1 times 3, 2 times 1, 2 times 2, 2 times 3, 3 times 1, 3 times 2, 3 times 3. Okay, so if you realize, guys, that the diagonal of this matrix equals what? The square of the values. Correct?
Mhm.
And this matrix, guys, is a symmetric matrix. You see, this is equal to this one here is equal to this one, and this one here is equal to this one here. So this, what we call this matrix here, guys, is the variance covariance matrix. The variance covariance matrix. So this is the notation of a variance covariance matrix. Okay, so the variances are going to be basically these elements here, the square of the numbers, and the covariances are going to be the elements outside the main diagonal. And that's the way we create a variance covariance matrix, this one here. Okay, so let's do this here. So E times E, and the other one can be E times E prime. Here we go. The main diagonal are the elements square of this one here, and the remaining ones are the kind of covariances. Now, if I want to extract the diagonal of a matrix, guys, what we do is we simply use I need to create a matrix first. So let's create this E1. If I do diagonal of E1, what I obtain is my elements in the main diagonal. Okay. Make sense? Okay. So let's continue. Give me 1 second, please, guys. Give me 1 second. Okay, so let me save this one here. Okay, guys, so let's go to talk a little more about other things that we use in linear algebra. Do you remember the determinant of A? If A is 1, I'm sorry, 1, 2, 3, 4. Do you remember the determinant of A, guys? Why the determinant was crucial, guys? So let's assume that you have the following matrix: 3x plus 2y equals 1, 6x plus 4y equals 2. Can you find x and y, guys? This is a very simple system of equations. Can you find x and y?
Yeah, you can.
Okay, can you give me the values?
Me specifically?
Yep. No, no, no.
Oh, okay.
You all, yes. what is going to happen there, guys? So let me tell you, we're going to do systems of equations later. I can write this one here in a matrix form. So what I can do, this can be 3, 2, 6, 4, that multiplies x and y, that is equal to 1 and 2. Do you agree, guys? Matrix notation of this system of equations.
Yeah.
Okay. Do you remember how to find the determinant of this very simple matrix? So from here, guys, the solution, if I call this A, I call this matrix X equals, let's call V. Okay. So how do you find X? X is going to be simply equal to A minus 1 times B. Okay, this is the inverse of a matrix, guys, and it's extremely useful. And the inverse of a matrix equals the adjunct of the matrix A divided by the determinant of A. Okay? So that's why the determinant is crucial, because the determinant is the denominator of the inverse of a matrix. And the inverse of the matrix is used to find values of X in a system of equations. And in econometrics, guys, we have systems of equations. That's all what we have. So that's why the determinant of A is crucial. Now, let's use MATLAB to find the determinant of A. Can you type A? So my A now is going to be 3264. My matrix A is going to be 3264. Now, the determinant is the MATLAB command of determinant is determinant, DAT. Take a look to what happens. 0. So what happens if it's 0? Why is 0, guys? Because indeed what is happening here, take a look. Do you see the second equation here? The second equation is simply 2 times the first equation. Do you agree with me or not?
Yes.
So
Yes.
indeed, you don't have 2 equations. You have 1 equation and 2 unknowns. So the number of potential values for x and y are infinite. So there is not a unique solution. Do you agree with me? And so now take a look to what happened in matrix notations. If the determinant of A equals 0, what happens with this one here? Any number divided by 0 is what?
Infinite.
Not defined. Do you agree? If you divide any number, 2 divided by 0 is undefined. Correct? So if your determinant of A equals 0, you cannot solve this system of equations. Got it? So when determinant, so there is one name here, guys. If determinant of A equals 0, we are going to say that A is singular. Obviously, if determinant of A is not 0, the matrix A is not singular. Makes sense to you? Do you see the importance? So this is mathematically, guys, we say that this matrix here is not linear independent. Because simply one is 2 times the other one. This one here is 2 times this. This one here is 2 times this. So when a matrix has elements or columns or rows that are not linear independent, the determinant is going to be equal to 0. If the determinant is equal to 0, I'm not going to be able to solve a to the minus 1. This is going to be undetermined. And as soon as a to the minus 1 is crucial to determine the values of x in a system of equations, I simply cannot solve a system of equations that have the determinants are equal to 0. Okay, so this is crucial, guys, for econometrics. I will show you later how this works. Okay, let's do some properties. Let's define A as 2, 1, 3 to just any random numbers. Okay, guys, 4, 5, 6, and let's do 7, 8, 9. Can you please find the following? Find the determinant of A show that determinant of A equals the determinant of A prime. Let's assume that you create A1, and A1 is going to be let me change something here. Perhaps I can do, yeah, I will do 158. So what I'm doing is I'm shifting one column. Find the determinant of A1 and compare with determinant of A. Multiply first column of A times 5. So let's call this A2. This is matrix A2. Find determinant of A2. Compare with determinant of A. Multiply whole matrix A by 5. Call this one A3. Find determinant of A3. Guys, very quickly, please, okay? And compare with determinant of A. Let me create my matrix. Let's create another matrix A that is going to be equal to so this is my matrix. Two minutes, guys. We need to run. We have a lot of material to cover. Okay, so let's continue. Do you see my MATLAB, guys?
Yes.
Okay, so what we're asking is, okay, let's find first the determinant of A, right? So, oh, sorry. -9. So -9 implies that this matrix is not singular, so you can do A minus 1. Okay, the inverse of a matrix. This is good. Now, what I was about to tell you, we can change one column, right? That's what I told you. Yeah, the second column becomes the first column. I will do something very quickly, guys. I will call this A1, and A1 equals A, right? And I want 2, 1, 3, all rows. Agree with me or not, guys? I can do flip up left and right. I can do whatever I want, but just let's do it. Let's do it quickly. Make sense? So what I shifted is the second column, put it in the first column. Now let's compute the determinant of A1. You see what happens? Simply shifting columns or rows, what it does, it doesn't change the determinant. What it changes is the sign. So if I do another change of column or rows, this is going to be negative. And if I change again, this is going to be positive. So it's going to be changing between positive and negative, but the number, the absolute number is going to be always the same. The next one, I will multiply, I will create, okay, so multiply by 5. So I will have A2 equals A. The first column. So A5 equals 8. What else? Okay, let's call this one first one, and then A2, everything comma 1 is going to be multiplied by 5. Correct, guys? Wait a second. So what I'm saying is, sorry, what am I doing here? This one, I want this one here. Sorry, what I'm doing, what I need here. I need to multiply the first column. Oh, sorry. So A2 is this one here, guys. Do you agree? Is this correct? This is A. So now A2 equals A. First of all, I want to be sure about that. A2 equals A. And then I will want to multiply A2. Okay. What I need to do here, guys, I just want to multiply the third column multiplied by 5. So how do I do that? Guys,
All rows,
all rows,
comma, the third column,
the third column,
close parentheses, times
yeah,
5.
times 5. But what's going on? I want this part here to be part of A2. So what I want is A2 to be like that. I want all these ones here multiplied by 5, but preserve this one here. How do you do that? Okay, 2 minutes, 1 minute to do this. Very quickly, guys. So what I want to tell you guys is simply this one, A2, everything, comma 3 equals This one here. Do you agree with me or not? So I need to open the complete matrix. And what I'm telling you, from this matrix, all rows, column 3 equals this part here, X. Do you agree, guys? So when you do only this part here, what you are doing is you're creating a new vector, basically. But you want to assign this vector and replace this vector with column 3. So that's why you get this one here. Then we can use the determinant of A2. And then I have minus 45. So this is equal to what? This is equal to the original determinant times the scalar. So now what I will do is I will create A3 that is going to be equal to A element by element multiplication times 5. Then I compute the determinant of A3 and I have 1, 1, 5. What is this one here? Guys, this one here is equal to 5. So the number that we're multiplying to the power of the rank of A3. Oh, I need to multiply. No, multiply. Power. And multiplied by the determinant, the original determinant of A. Okay, always there is a relationship. You don't need to really memorize this stuff. But what is the rank of A, guys? What the rank measures? The rank measures simply the maximum number of columns or rows that are linearly independent. Okay, the number of rows or columns that are linearly independent. So this is the rank of A. So in this case, no. In this case, we have all the columns and rows of A3 are independent. So we can use this for solving an equation. Now let's go to the inverse. Where's mine? So this is the determinant. Now let's go to the inverse. I will just give you inverse of a matrix. Okay, so this is denoted like A to the minus 1 or inverse of A. Okay, A to the minus 1 is A minus 1. Okay, some properties. Okay, so A find A to minus 1 of this A that we have here. Some properties, guys, show that A times A to the minus 1 is exactly the same as A to the minus 1 times A, and this is equal to the identity matrix. You can start working, please, guys, very quickly. Show me that A prime to the minus 1 is exactly the same as A to the minus 1 and then prime. Yeah, that's it. We don't need more. One minute to do this is very quickly. Okay, let's do this very quickly. So I want to call my matrix A. The inverse of A is this one here. Then I ask you, yeah, A times A prime. So let's take a look. So let's do A times.
Professor, we can just see paint, not
Oh,
MATLAB.
yeah. Now, do you see my screen?
Yeah.
This is my A. Inverse of A is this one here. Now, what I want to prove is that A times inverse of A equals what? The identity matrix. And it's the same as inverse of A times A. So this is always the case, okay? Next is, yeah. So let's do inverse of A prime up there. It's not A, it's A. And now let's do inverse of A prime. You see, guys? This is exactly the same. Make sense? Questions? Okay, let's do a system of equations now. And you're going to solve them. Let's assume, guys, that I have x1 plus 2x2 plus 3x3. This is equal to 366. 4x1 plus 5x2 plus 6x3 equals 804. And I have 7x1 plus 8x2 plus 0x3, I'm explicitly here, equals 351. So find x1, x2, and x3 using matrix algebra. Basically, what we did here. You need to build this matrix, and then you find these values here. Okay, guys, 2 minutes to do this. Okay, guys, let's do this, okay? So let me write, let me copy this one here. Okay, so 3. So I will call it matrix A also, and A is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. Okay, so this is my matrix A. Do you agree, guys? So what I'm doing, what I want is this one here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 0. That multiplies x1, x2, and x3. And this is going to be equal to 366, 804, and 351. Do you agree? So this is A times X equals B. So what I need to create now is B. B is going to be equal to 366, 804, 351 transposed. And then that's it. How do you solve the equation, guys? How do you find the values of X? Here, first of all, X is going to be equal to what? What I do, guys, is I do this, correct? So do we know what is this? This is Ix equals A prime, A minus 1B. Any matrix multiplied by I is the same matrix. And so basically what I'm saying is this one here. Correct? Agree with me or not, guys?
Yeah.
Okay. Then X is going to be equal to the inverse of A multiplied by B. Here you go. So X1 is 25, X2 is 22, and X3 is 99. There is another way of doing the same, guys, that is this one here. So instead of doing inverse, is A. This is based on Frobenius norm. This is another technique, okay? This is another numerical mathematical technique that instead of using inverse, we use something that's called a norm. And the way to do that is A, the backslash B, and you see this one here is more efficient. But for us that we do econometrics with limited data in economics, guys, we're indifferent. You don't see the difference. But if you have a huge data set, you can save a lot of minutes using this notation than this one here. Okay? So, okay, so you do the following, guys. Talking about the norm. In MATLAB, guys, let's assume that I have a matrix X, 1, 2, 3, 4. Okay, the norm is defined as the square root of X primes X. You take the diagonal, and then you sum. And then you take the square root. So basically, do you remember, guys, when I do X times X, what do I get? What the main diagonal of this one here is going to be what? The main diagonal. We have mentioned this before. It's going to be the square of the elements. Do you agree?
Yes.
Okay, remember, guys, there are two ways of measuring distances. Do you remember? If I want to see the distance between one point, let's say 3 and 5, how do you measure the distance? How do we measure this distance? Guys, come on. It's going to be 5 minus 3. Agree with me or not? So the distance here is 2. The problem is that if I go from 1 to 3, my distance is gonna give me 1 minus 3. So the distance is going to be minus 2, and the distance here is going to be 2. But remember, distances cannot be negative. So what do we use? There are 2 techniques to be sure that we have positive numbers always. What are these 2 techniques?
Absolute values.
Yes, absolute values is one of them. And the other one? We square the numbers. So we use this a lot in econometrics, guys. That's why we do minimize the sum of square of the errors, etc. Got it? So what we are doing here is we are finding that the distance of a matrix is normally measured by the square of the elements of the diagonal. Then you take these elements from this matrix and then you sum them. And then you take the square root. Okay, and the positive side of the square root. So this is basically the norm. It's a measure of how dispersed the data is. Right? Can you create your norm? Just give me your norm. Use this matrix, use this notation, and create the norm of X. So A, create the norm of X using the formula. And let's do B, use this MATLAB command, norm X Frobenius. So, sorry, this is the Frobenius norm. Okay, very quickly. Have we done that, guys? Let's call our n. And it's going to be square root, sqrt, of sum of the diagonal of, x prime x. Yeah, but I haven't defined x. So let me define, it's not this x. So let's define x as, I said what? 1, 2, 3, 4. I don't know if I define this one. Okay, so now I can apply my formula. The square root of sum of the diagonal of x prime x. I have 5.4772. Do you get the same number? Guys, you get the same number?
Yes.
Okay, so now if I use the MATLAB command norm of x Frobenius, the same number. Okay. Now, let me do what was my A? I want to use perhaps this A. There are a couple of things, guys, that you need to learn in order to optimize your programs when you do econometrics, okay? And one of them is based on the eigenvalue. Let's do first of all the eigenvalue. So let's call this D, and the eigenvalue, I will explain what is the eigenvalue, but I just want the properties. So what I compute is the eigenvalue. So when you do a co-integration analysis, for example, you use this technique, finding the eigenvalues, and you find the eigenvalues that are above zero, for example. Or when you do k-means or cluster analysis, you use this type of eigenvalue analysis. Okay. At this point, what I'm interested is the following: you have a matrix A, and then you find simply the eigenvalues. And why the eigenvalues, guys? The eigenvalues have beautiful properties. Can you just take a look? Do you remember what is a trace? Do you remember what was the trace, guys?
Some of the elements in the
In the main
diagonal.
diagonal, right? Yep, here you go, 6. Now, if you take a look to the sum of D, so the sum of the eigenvalues equals what? The trace of the matrix. The number of eigenvalues different from 0 equal the rank. How can I find that? Can you find the number of eigenvalues different from 0, guys? Of course, you see this is 3, right? But I want you to use all what we have learned. You can use the operators, relational operators to find that. Tell me how many elements of D are different from 0. Guys, please, during the weekend, you need to review all what we have done, okay? Otherwise, it will take a lot of time to do more programs. So, okay, we need to run a little. Do you remember what happens if I do this? D not equal to 0. Do you remember what we're going to get here? We're going to get the vectors of zeros and ones when the condition is satisfied. 1 if the condition is satisfied, 0 if not satisfied. Do you agree?
Yes.
Okay, so then what I can do, as soon as I have zeros and ones, what I can do, I can sum these ones. So basically, what I'm saying is that this is going to give me 1, 1, 1. Is different from 0, yes. Different from 0, yes. So it's going to be 1, 1, 1. And then I sum these ones here, and I obtain the number of elements of D that are different from 0. And this one here, guys, the sum of, the number of elements of the eigenvalue that are different from 0 equal the rank of the matrix. And finally, guys, the product of the eigenvalues, oops, no, yeah. The product of the eigenvalues equals the determinant of the matrix. Okay, so there is one property of matrices that is AB equals BD. So these are my eigenvalues, and these are my eigenvectors. Okay, how do we compute this in MATLAB? Simply EIG of A. Okay, please do this. We have A already. You're going to compute B and D using this one here, and show me that indeed this is true. AB indeed equals BD. So B comma D equals the eigenvalues of A, right? And then I know that A times B should be equal to B times D. Do you see? Do you see this one here, guys? So why this is useful? Of course, now that we know that this is true, it's easy. It's a piece of cake, right? But the one that created or discovered this type of mathematical formulas, who discovered this identity, guys, was a genius, because this was discovered more or less in 1600. Okay, it was developed by, I don't remember who, but he was a genius on doing this stuff. Why? This is crucial, guys. This is crucial for the following. Let me work a little with this one here. And you tell me if this is wrong or not. BD. What I will do is I can do the following. I can do B times B minus 1. And just not to modify, I do this. So a matrix times its inverse is the identity matrix. So this is going to be A equals B D B to the minus 1. Okay, so this equation, guys, is one of the equations that is one of the most important equations on linear algebra. Why? Just take a look to what happens. A squared. A squared is going to be B D B minus 1. Again, B D B minus 1, right? A squared, A times A. So let's develop this one here. It's B D B minus 1, B D B minus 1. Now, this one here is the identity matrix, disappears. So this is equal to B D D B minus 1. This is a diagonal matrix. Okay, when you multiply two diagonal matrices, it's simply the square of the elements on the diagonal. And here you go with this famous equation, guys. How do you find quickly any power of a matrix? You find the eigenvalues, and then you simply do this equation. So in general, A to the power n is going to be equal to B D to the power n, B to the minus 1. This is this. Okay? Show me, guys, that indeed A times A is equal to B D squared B to the minus 1. This is times. Okay, show me that very quickly. And just remember this formula, please. Okay, so let's do this. A times A, agree? And now what I will do is I will do B times D power square times inverse of B. Do you agree, guys?
Yes.
Perfect. And we can also we can also generalize this one here, guys. Is that, for example, a to the minus 1 equals b, d to the minus 1, b to the minus 1. Can you verify that? So this is what is called eigendecomposition. Eigendecomposition. So again, my inverse of A, and by my eigendecomposition is B times inverse of D times inverse of B. You see that? So this methodology here, guys, is much simpler. I'm telling you, it's much, much simpler than finding the A minus 1. So finding the inverse of A by hand is a pain in the neck. Do you agree? Have you done that before? Have you found the inverse of a matrix by hand? Yes, a 3 by 3 is already a pain. Guys, so if you want to do an inverse of a matrix that is 10 by 10, it's almost impossible to do by hand. But we're talking about the 1600s. If they need to do it, they need to do it. But this guy discovered this methodology, and finding the eigenvalues and eigenvectors is extremely simple. Right? Once you have your eigenvalue, eigenvector, you simply do this technique here, and then you find these values here that are exactly the same as the inverse. Okay, guys, questions? Okay, so for this weekend, you're going to have the second assignment. I will give you the third assignment, and I will give you a fourth assignment. So you're going to have 3 assignments for the weekend, plus something that you need to start working on. Okay, let me show you my screen. I will give you, guys, I will give you this very simple summary of the Euler's model, the ordinary least squares model. Have you heard about that, right?
Yeah.
Okay, so here we have, for example, I know you know the formula of beta is x prime x to the minus 1 x prime y. Then you can have all these coefficients. You have the formula for the r squared. How do you compute the r squared? How do you compute the r squared adjusted? How do you compute the variance of the errors? That's what I want. Yes, and then here you have an example, guys. Okay, imagine that we have 5 observations. Okay, this is my y, this is my x1, and this is my x2. You know, what is x prime x? I show you how to do this stuff. What is x prime x to the minus 1, etc. Right? So you have all the notations. What I want from your model, guys, is to compute, to just start thinking about computing the betas, computing the r squared, compute the r squared adjusted, and these coefficients. Later, we're going to do the standard errors, etc. Make sense? I will send you this file also. And I also will send you a file in Excel with a numerical example. This is not, you need to do 2, 3, and 4 for sure. And this one here, you just try to understand the model and try to start thinking how to do this in how do you call it? How to do this in MATLAB. Okay, so I have here the data. I have run the model with Excel, and then I do here the algebra. Okay, x prime x is this part here. X prime x to the minus 1 is this one here. No, then you compute your x prime y. Then you compute your a, b, b1, and b2. So you have the formulas. Understand the model first of all. The variance of the errors, etc. understand this Excel. So your assignment for next week is simply to understand the mathematics that I'm gonna give you in here. Very simple. It's very straightforward. But what is more important for me is you to understand how the algebra works in OLS. Because the next model we're going to create in programming is going to be the simple OLS model. And you're going to be able to create your own OLS model with this one here. And then we're going to move into more complicated models, but you're going to see it's not complicated at all if you understand this model. Make sense?
Yes.
Okay, questions, guys? No questions? Please, guys, you need to study just language. Remember, MATLAB, Python, or whatever are languages. So languages implies that you need to learn the language. So you need to memorize first some commands. Okay, you need to understand how to do M files. You need to do how to link M files. You need to do the homeworks. The homeworks are going to help you do that. And well, in this part here, you need to know how to use a linear algebra to create some outputs. Make sense?
Yep.
Okay. Okay, guys, we stop here for today. It's almost 8:30. I think we have done what I needed to do. Next week, we are going to start working with interactions of Excel files. We're going to start uploading Excel files, exporting Excel files, and doing more serious data analysis and moving from there. Got it?
Sounds good. Thank you.
Okay, guys. Have a good night. Have a great weekend. See you
Thank
soon.
you.
You
You too.
You guys.
too.
Thank you so much.
Thanks.
Bye.
Bye.